Good morning, everyone. Well, it's a little cooler today, but it's not 11 degrees, so I'm grateful for that. I hope everyone's doing well and getting back into a somewhat secure routine. Um, it's always nice to not worry about too many bumps in the road. We like it when things are a little bit more peaceful, and I would say, controversy and difficulties are good. They make us better, they help us grow, but sometimes it's great to have a little break so we can, uh, you know, feel, sane again. So, what I want to do today is to say a little bit more about the equations, do an interest type problem, and then talk about changing the base for exponential functions. And then I want to cover the basic models from 4.6. And of course, one of the models you did in college algebra, the instantaneous growth and decay, and then the other model will just be the Newton law of cooling. We're not going to actually discuss so much the calculus of the uh, models. We will use the solution curves. And so the act of actually using the result of the differential equation is something we can do in pre-cal and college algebra because they require the basic knowledge of the logs and the exponents. So I think that will be interesting to you. And of course, something that you will study more when you take the calculus sequence, and then those of you that go on into the STEM, into the engineering and mathematics, we'll take differential equations and see it again. So the nice thing about math is that we do repeat things. So there's always an additional opportunities to get that much better at it. And of course, we'll have our test before spring break next week, but I have good news. The test will conclude with the logarithms and exponents. We will begin our study of trigonometry on Thursday. I may say a little bit about it today, but I doubt I'll have time. And so there will be homework that you will have from this week from the WebAssign, but none of that will be covered on the test. So the third test that you take after the break will just be completely devoted to trigonometry, which is good. Just, one topic, which makes things a little bit easier. So I always like to share that news with you just to give you a little bit of a breather, to give you time to get accustomed to some of the concepts that we're going to be dealing with trig, but not feel like you have to just, go out there on a limb and start working with it on a test. So that should bring you some relief, because I know you have other classes and other obligations, and math is, of course, a big time consumer just because of the nature of the subject. So let's go ahead and get started. Like I say, what I want to do are some examples to finish up the equations and then move on into the models. And it's good to see everybody this morning. Everybody's always so kind to say good morning. And indeed, it is a good morning. So let me share my screen. Now, like I was saying, I kept saying last week, I said, well, I'm going to do this interest problem, but I kept finding other things to do. So let me go ahead and write this. Very straightforward, but because we have some new techniques with our solving of equations, we can work this with relative ease. So here's an example. So we have compute the time for $5,000 to grow to $8,000 at 7.5% annual interest, compounded quarterly. So again, this uses the concept that we derived last week with the compound interest. And so we want to solve for t. So basically here, I'll just write in parentheses, solve for t. So before we look at the actual formula, let's just deal with the interest and get the base set up. So we have 7.5%. And of course, we can just write this as a fraction. This is 7.5%. And then of course, this is just 14 plus 1 or 15 over 2%. And then we can write the percent as a fraction by dividing by 100. Of course, what we always do. So we have 15, 2 times 100. And of course, we can factor 3 times a 5. And then we have 2 times a 20 times a 5, obviously. So 5 divides the 15 and the 100. The 5's absorbed, and we're left with 3 over 40. So that's our interest rate as a fraction. Again, when I get questions from you about rounding, it's because your work is not exact. When you're doing problems like this, you must keep exact computations to the very end. And then if WebAssign asks for an approximation, then you can make it that very first time with the Google calculator and not have introduced round off error before that. So like I keep saying, you find out when you work a quiz that your numbers are off because you rounded unnecessarily. So I don't teach that way. I teach you this way. So please be careful with that and try these techniques so that your work is less error prone. So now what do we need? We need 1 plus r over n. It's good to just kind of set this up like we're doing a quadratic equation to get ready for the punchline, so to speak. So this will be 1 plus, we have 3/40, and n is equal to 4 because we have quarterly, so we have 4. So what's interesting about this particular type of computation is that we keep everything, like I say, exact, and we don't have to worry about introducing round off error. So now what is this? Invert and multiply. So we have 1 plus 3 divided by 4 times 40. So this gives us 1 plus 3, and 4 times 4 is 16 with a 0. And so our base will be a rather strange number. So that'll be 160 plus 3, which is 163. So we get these rather odd looking bases with these interest problems, but that's okay. What I'm going to show you sometimes is instead of worrying about taking a logarithm to that base, we'll often just execute natural logs or base 10 logs, excuse me, to keep the arithmetic a little simpler. I mean, again, logarithms are very flexible, so you can do whatever you like. So now this implies we have our interest formula. So the growth is 8,000. And this will equal the principal, 5,000. And then we have our 1 plus r over n, which is 163 over 160. And we raise this to the nt. So t is the unknown, and n, of course, we have as 4. Let me just go ahead and notate this in red, just to kind of circle that. We've already used that, and I think you know that, but that's a 4. So we get 4t. And like I said, we want to solve for t. So this is basically an equation that we can easily solve just by basic techniques that we've already learned. So now, notice when we divide by 5,000, all the zeros absorb except the 8 and the 5. So we have 8 over 5 equals 163 divided by 160 to the 4t. Again, all the execution here is exact. Now, at this point, just to make the work a little bit simpler, pick your favorite logarithm. And usually with interest problems, I'll just use the natural log. So at this point, and we'll do this often today, take natural logs. Again, why do we care about the natural logs? Well, when we take the natural logs, we can actually apply the power rule. We can bring the 4t to the coefficient level and be able to solve for t. So now we have 8/5 natural log. And I'll do this in 2 steps, even though you can usually consolidate it. Natural log 163 over 160 to the 4t. And now, of course, by the power rule, this will work for any base or any power function. The 4t comes down. So we have 4t times the natural log of 163 divided by 160. Now, if you like, just to make it a little more user-friendly, pull the t off to the left. You don't have to, and put the coefficient inside the brackets. 4 times the natural log of 163 over 160. That makes the work a little bit easier to see. So now we have t times a number equals a number. So that's like saying 3x equals 5 or 3t equals 5. So let's just divide by that coefficient. So if and only if t equals the natural log of 8/5 divided by 4 times the natural log of 163 over 160. And when we look at this, let's see, let me check here. Okay, right, good, good. You got the quarterly part, excellent. So now when we look at this, say you're doing a WebAssign problem, this is exact. So we can say this is exact. Now on the test, there might be times when I'll say, okay, I want the exact time, and I won't ask you to approximate it, and the answers will have this type of form. So it's really important that you learn how to compute in the exact mode. When you're doing science problems, when you're doing computer science problems, computer science is very tricky. And everybody in computer science, you want to deal with decimals, and round off error is just a huge issue. That's one thing about the computer algebra systems that took the computer computation to a new level. We have to avoid the excessive use of decimals unless we just run them out to so many places that we don't have to worry about round off error. But that just gets extremely messy. So when you're doing your computations here, you really need to stick to exact computation. Now, at this point, you can use your Google calculator and get a nice approximation. For instance, in this case, maybe WebAssign would say the following. Once you get your exact, you could say round to 1 decimal. So at this point, with the Google calculator, let me just go ahead and pull that up. Let's see here. Okay, I don't need that thing. Let me go in here and go to Google. Okay. So let's go back. Let's see if it sees. Oh, good. Sometimes it doesn't see the Google calculator. I have to move it around. So now we go to Google. And so we'll have natural log of 8 divided by 5, close, then divided by, use parentheses, 4 times the natural log of 163 divided by 160. And then, of course, close the parentheses of the log and then of the character string in the denominator. And this will give us 6.32528. 6.3258. And that would be enough. See, for instance, a lot of times when we do trigonometric calculations with triangles, we'll have to keep the calculations exact. Otherwise, you get horrible round off error and students just start to lose their mind. So now this would say to one decimal, 6.3, in this case, years. So this is, always reminds us of the fish population back in 1.5. The idea, again, the idea here is we prefer the exact, okay? We always prefer the exact. I'm not really sure about the world's love affair with decimals. Decimals are great, but as long as they're exact, as long as they're exact approximations, we always like to have an expression that gives us the full detail. And this is important. It is very important to be able to compute in this way. If you can't, you get to Cal 1 and Cal 2 and you start to struggle. So this is exactly why I prepare you for this. I teach students that in the calculus sequence that don't take me for pre-cal, and they always say, well, I wish I would have been around when you were teaching pre-cal. And I'm like, well, here's the thing, ladies and gentlemen, when you learn a subject, you learn it. You don't look for shortcuts. Some of you sometimes say, thanks for the shortcuts. Well, the shortcuts are good mathematics. If you approach your problems with good mathematics, what seems to be a shortcut is really the execution of a bona fide mathematical strategy. And that is what we want to do. And we don't want to sacrifice accuracy because we just want to punch buttons on a calculator. You work the problem, and then at the very end, you do an approximation. That's the way that you do mathematics. And it's not unfortunate that you have to adapt some new techniques. That's part of learning. That's what we do every day. I mean, it's amazing. Everyone says, all academicians say, well, learn something new every day. Well, we learn something new every day, whether or not we try. That's just part of living. So I guess you could make a concerted effort to learn something in every subject you take. That might take a little bit more effort, but it usually just comes through osmosis. Now, what I want to do is look at another equation and talk about, I've shown you the formula and actually had some conference hours on Friday where I worked with some of your colleagues with some logarithms and some rational functions. And so you know that we have a formula for change of base for the base A logarithm. So what I wanted to do was share a formula that uses the logarithm to give you a change of base for the exponential function that's easy to use. And I want to do it with reference to an equation. So here we've got, I just pulled this out of your e-text. So we have 2 to the 3x plus 1 equals 3 to the x minus 2. Now, when we look at this and we think about this particular problem, first, what we want to do is note that we can't use the one-to-one because the bases are different. It's like having two logarithms with different bases. That we're going to have to change the base if we want to set the arguments equal or the powers equal. So I just wanted to share with you a change of base. It's easy to write. Change of base for base A exponential functions. And I guess you can, whatever base you want to call it, exponential functions. So remember, we start with base A, and then maybe we convert to base B. That use any letters you like, A and B. I guess they're just convenient. So for instance, we could say we'll use the inverse property of the logarithm and the exponential. So we could say A to the X. And then the trick is to just say, let's place this with the base B logarithm. That is, we can say B to the base b logarithm of a to the x. Well, b and the base b logarithm undo each other, and we just get a to the x due to the inverse rules. And so then we can apply the power rule, and this just gives us b x to the base b logarithm of a. So we kind of work backwards from what we learned about logarithms to affect this. So now we can see that if we want to change the base, we can simply write the new base and then the power times the logarithm coefficient, just like we had with the coefficient in the denominator of the logarithm change of base, the base b log of the old base, so to speak. So this is again what you will do in calculus. In calculus, we will just always convert to base E. Base E is the base of calculus. So we'll just say, I'll go ahead and let the cat out of the bag. When you get to it, you'll like, oh, I've seen this before. In calculus, we write a to the x and use the natural base. So we'll just say E to the x ln of a. So for the calculus version, we only produce the calculus for the base E, or the natural exponential, and then we can again transfer it to any base. So we see from here, we just do a specific b, which is the natural base. So this is the construct that you will use often in calculus, just like the one I gave you for the logarithm, changing to the base E logarithm. So again, you see it's all connected, it's all related. So what I want to do is ladies and gentlemen, I want to do this problem two different ways and show you that it doesn't matter how you do it. So when you're solving an equation on a quiz or a homework or a test, and your friend solves it one way and you solve it the other way, and you end up with an equivalent answer, then that's fine because you use good mathematics. So for instance here, let's just say that we have base 2 here and we want to change this to base 2 so we can set the powers equal. So here we'll say 2, 3x plus 1. And now we're going to change this to base 2, so we'll use this construction here. So this will be 2x minus 2. And now we have base 2 logarithm of 3. So here we see that the b has been replaced with 2. The new power is x minus 2, and the old base was 3, as we see here. So, and this is interesting. Several years ago, I had a college algebra class, and I said, well, how do you want to solve this? And the young lady said, well, let's just change the base. And I thought to myself, you know, that's perfectly fine, because I thought what everyone was going to say was just pick your favorite logarithm, use the power rule. And when she said that, I said, you know, good idea. Why not? Let's do it. So that was kind of the beginning of Professor Ron, and I've always done this, but since I've been at San Jac, you always listen to your students and their ideas, because it's very often that a student will be basically referencing an idea that many other students in the class may have. And I said, well, good, you get 5 points for that. So let's do it. So now notice, we see that the bases are aligned, and so we can set the powers equal. So equivalently, using 1 to 1, 3x plus 1 equals, now of course, this is just a number, the power of 2 that equals 3. So we'll just multiply the base 2 log of 3 by x and 2. So we have x times the base 2 logarithm of 3, and then minus 2 times the base 2 logarithm of 3. Just go ahead and multiply that out. Again, remember, a logarithm is a power of the base. So when you have all these letters here, they just signify one number. So don't think of it as extra stuff. It's just one number. Excuse me. So now let's just put all of our x's on one side and our non-x terms on another, like we're solving for an inverse function. So we have 3x minus x times the base 2 logarithm of 3. And now, of course, let's just subtract 1 here. So we have negative 2 base 2 logarithm of 3 minus 1. Now, when you look at this, you're thinking, well, this is really good. This was kind of like the question we had with the interest. So we can just factor the x here. So x, 3 minus the base 2 logarithm of 3. And of course, all these negatives, we can multiply and divide by a negative to get rid of some of them if you want. It doesn't matter. You can leave them in there, but usually we get tired of them. So now we have x times a number equals a number. So we can divide by this number. So x equals negative 2 base 2 logarithm of 3 minus 1 divided by 3 minus the base 2 logarithm of 3. Now, of course, like I said before, you get a little bit tired of all of the negative signs, so you can multiply and divide by negative 1. I've done this many times just to clean it up a little bit. So this gives us 2 base 2 logarithm of 3 plus a 1. And then, of course, downstairs, they just flip around. Base 2 logarithm of 3 minus 3. And of course, the exponential functions are nice and happy. They work for all real numbers as long as it's a bona fide real number. So this is a legitimate solution. Logarithms are a little bit more specific. We have to make sure that the argument turns out to be positive, okay? You can always, once you process the argument, the number to which you are applying the logarithm must be what? Must be positive. Cannot be 0, cannot be negative. So now when you look at this, you're thinking, okay, well, Professor Ron, what if we had done it that other way that you suggested by like taking natural logarithms? Do we get an equivalent answer? So what I want to do now, just as practice with the change of base for logarithms, is just go ahead and convert this to the natural log by using change of base for logarithms. So let's go ahead and do that. Then we'll solve it another way and show that we get the same answer. Of course, this is equivalent. It just looks a little bit odd. So now we have 2. So we're going to do the change of base to the natural base. So we'll have natural log of 3, little times there, divided by the natural log. Now, notice here, when we do this, we have the natural log of 3, which we actually change up here. And then you're thinking, okay, so what do? We take now the natural log of the old base. So this will be ln of 2. And then over here, we've got a plus 1. Let's do the same thing here. It's going to look the same. We're going to convert to base e. So we have natural log of 3 divided by the natural log of the old base, natural log of 2 minus a 3. Now, of course, let's just go ahead and get a common denominator so the ln's of 2 will absorb. So we get 2 ln 3 plus ln 2 all divided by ln 2. And here we'll do the same, ln 3 minus 3 ln 2 divided by ln 2. Now, of course, when we invert and multiply, these guys absorb. And so this leaves us with 2 ln 3 plus ln 2 divided by ln 3 minus 3 ln 2. So what I wanted to do here, again, this is also x in a different form. So for instance, if you were doing your WebAssign and you solved a problem like this, you just use your subscript on your bases and type that, be done with it. If you did this method, okay? Now, the reason I've converted to this we will think of as method 1, method 1. Now, another thing that's very popular is kind of like what we did with the interest problem and what we'll do with some of the modeling problems with the instantaneous growth and decay. So what we can do in this case is now start the problem by taking natural logs of each side. So here's what we're going to call method 2. So let's start with the original equation, then I'll have to move to another sheet. So let me just do this. I'll just say we'll do this and then I'll come back to this to compare. Let me go ahead and put this on a new sheet. That way we won't be running out of paper. So we'll just call this method 2. So our equation is 2 raised to the 3x plus 1 power equals 3 to the x minus 1, or x minus 2, excuse me. So now method 2, and I'll do this in red, just like we did with the interest problem, and we'll do later. Take natural logs. I'll use the same base so we can compare. Of course, if you don't like the natural logs, you can take base 10 logs, log. So let's do it. So we have ln of 2 to the 3x plus 1, and we have ln of 3 to the x minus 2. So for instance, if you're just thinking that you're like in a physics class and you just want to go ahead and get an answer that's all ready to go, maybe you don't want to have to change the base, and you know your calculator has a base e key. If your professor says, okay, give me a 2 decimal approximation, you may prefer this method. So now we can see that we have the natural log of a power of an exponential function or power function, which also is true. The power here will now descend. So we have 3x plus 1 times the natural log of 2 equals, again, descend, x minus 2 times the natural log of 3, okay? So when we think about this technique, many students like this because it's just natural to use the natural base. In calculus, of course, everybody just runs to the natural base. So that's a wonderful way to do it, and certainly good mathematics. So now what we'll do, like we did before, is go ahead and distribute the natural log of 2 and the natural log of 3. So I'll put the x first. I'll say x times 3 natural log 2. And then, of course, natural log of 2 times 1 is just natural log of 2. Now here I'll do the same, just since I'm writing it that way. I'll just say x times the natural log of 3, or you don't have to put parentheses. I'm just trying to emphasize the point that that's a number, okay? So we make our work really clean. And then minus 2 times the natural log of 3. Now at this point, we can remove all of our x's to one side. And of course, you're thinking I could go this way and spare us having to multiply and divide by -1. But I want to do that again, just so you'll get practice with it. So we have x times 3 ln 2 minus x times ln 3. And of course, we can remove the log 2 to the other side and get -2 ln 3 minus ln 2. Now we can factor. So you see it's about the same number of steps, 3 ln 2 minus ln 3 equals -2 ln 3 minus ln 2. The computation is not difficult. It's just a little bit longer because we just have more algebra, but it's not difficult algebra. Now divide x equals -2 ln 3 minus ln 2 divided by 3 ln 2 minus ln 3. Now, of course, just like we did before, let's go ahead and get rid of the negatives, multiply and divide by the same number, rewrite it, we don't change it. So we get 2ln3 plus ln2. And then, of course, the negative here, we'll just flip this around, ln3 minus 3 ln2. So now when we look here, we have 2 ln3 plus ln2, ln3 minus 3 ln2. So the production of a solution, of course, is the same. Notice when we did method 1, we just changed the base. And by changing the base, we can use one-to-one property. And the one-to-one property just says we can set the powers equal, the exponents equal. And of course, we get this. Then we practice changing from base 2 to base E. So you're thinking, okay, well, for this problem, if we do the change of base to 2, our answer winds up in base 2. And then, of course, if we want to, just for reasons of maybe approximation, switch the base, we've got this. So it's really not that much extra work to do this. And when we compare the two, you might say, well, this is a little less work if we just go ahead and start with the natural log. So you can look here and just say, well, the base A logarithm, the power rule works for any base. So you might be thinking, I'll save a little bit of time and just go ahead and affect the solution execution using the natural log. So it's not necessary that you always have to verify that your particular solution is equivalent to another solution. Sometimes that's more tedious than it's worth. I mean, when you get to calculus, you'll notice with trig functions and logarithmic functions that there's plenty of variability in how solutions can be written, and you can spend many minutes trying to verify that things are indeed equivalent. You will learn in calculus that functions with the same derivative differ by a constant. That's the mean value theorem and has a huge impact on the execution of antiderivatives. So maybe it's a good idea to practice the execution of these types of techniques. So what I want to do now, and again, when you're working with logarithmic equations and exponential equations, you have open to you all the techniques that we've talked about from day one and all the techniques you talked about in Algebra 2 and college algebra. So don't feel like you are, stuck with any type of strategy. You can use good mathematics and get to an answer, get to the finish line successfully. So I've just tried to give you some techniques that I think hopefully will give you some new strategies, or maybe just remind you of the ones that you did in college algebra. And I know a lot of you had really good training in college algebra. So that's really good. I'm glad to hear it. Not a surprise. So now what we want to do is talk about two models that were basically discovered, invented by Sir Isaac Newton. And the first one, so this will be in 4.6. We'll just call these models. I guess we've already really been talking about some models. We just didn't derive them, or at least say exactly what they were. So the first one is instantaneous growth and decay. Sometimes they call this the growth and decay law. Instantaneous growth and decay. Now, when you solve a problem, they'll say this obeys the growth and decay law, and sometimes they call this the exponential law, exponential growth or decay law, exponential growth and decay. There's another way of saying it. When it's actually applicable, the problem will say that, and you'll know that you have to use it. We're only going to have two models outside of what we've talked about. It'll be this one and the cooling law. So it'll be clear that you have to use it. You don't have to sit there and wonder, well, what strategy do I use? Please don't overthink it. Just know that if you have problems that remind you of with this of this type of terminology, then you know what to do. We'll say DE for differential equation. And when I write it, it'll basically be something you can solve in calculus. And I'm going to show you some calculus for the Newton law of cooling, again, which will be very useful to you when you get to calculus. Just remember, folks, that we often will use a result like maybe the Descartes rule of signs to figure out the disposition of real zeros and also imaginary, even though we're just focused on real polynomials. That particular rule or theorem requires the use of Rawls' theorem from calculus. That doesn't mean we can't use it. It just means that if we were trying to think about why we're true, we need to learn a little bit more mathematics. So that's not a bad thing. It's actually a good thing, because when you get to the calculus, you can always research that and say, well, let me see if I can fill in the details and figure this out. So in this case, what we're going to have, I'm going to write the equation, then I'm going to tell you about some of the symbols. Basically, we're going to say the instantaneous rate of change of y with respect to t, that's a derivative, dy dt, equals a constant times y. And there's going to be an initial amount of y, which is a quantity, which we're going to call y sub 0. So let me go over here and say k will be a constant of proportionality. So you did your homework as a biologist and figured this out in the laboratory, so to speak. The laboratory could be anywhere. Constant of proportionality. And then y, what's y going to be? Well, you can use any letter. This will be the quantity, maybe it's a population, a mass of a radioactive compound, quantity to be predicted. So you're thinking, if this is the differential equation and we solve it, we'll have a formula for y. So I always call the solution to be the predictor. So y will be the quantity to be predicted. So we want our model to be like a fortune teller, to say if we input a certain time, then we will have a prediction of the quantity y. And then t will be time, and that'll be, maybe it's in minutes, maybe it's in years, days, whatever, time. And then, like I say here, y of 0 or y sub 0 will be the initial, correspond to the initial quantity. This is just standard notation and terminology for these types of equations. So this is why we say instantaneous. The instantaneous rate of change of y with respect to time is actually equal to the amount present times some constant of proportionality. So the change in y basically is proportional to whatever exists in y. I mean, it's proportional to y when you're thinking, and when I say whatever exists would be the quantity. So this is not something that you just wake up one day. Newton did some laboratory work and did many observations and basically said, oh, here's a rule. Here's a rule that I have observed in dealing with populations, maybe populations of certain organisms. And then you could think maybe he's dealt with other quantities like radioactive quantities, because he did a lot of work in chemistry. And so he thought, okay, well, here's my model, and it really does do a good job of explaining these situations. And then he said, since he actually discovered the calculus, at least was credited for it, then he would say, we can solve this equation. And here's the solution or solution curve. And this is what you saw in college algebra. And it's y will be y sub 0 times e to the kt. So that's why they call this the exponential growth and decay, because it turns out that the solution to this equation of derivatives gives you an exponential equation. So we have the initial amount times this exponential factor. Now, a lot of times when I work these problems, I end up solving for e to the k to change the base to keep the computation exact. And that again was something I instituted because I was tired of students having so much inaccuracy in the problems that they did. So again, like I said before, we can think of this as a study of some particular quantity, some type of quantity, be it a population or a mass or whatever. And if we do our homework and say, okay, well, we've tested this and it appears that this model is applicable to our particular scenario. And so then we say, okay, now what we're going to do is put in the initial factors here so that we can write the predictor. And then we can use the predictor to estimate future occurrences. So just like thinking about statistics, how statistics can predict, we can think of this as also a predictor. So let's look at an example. So here we have, this is close to home, so about populations of actual people. So we have the population of California was 29.76 million. This is exact. We take this as exact in 1990. And 33.87 million in 2000. And here we say, the problem says, assume exponential growth, this model here. So the problem will always say, use the growth and decay law, assume exponential growth. That clues you into this. So there's no guesswork there. Don't have to worry about that. The problem will give you the idea. Now, first, so A in this particular problem is, what is the predictor? What is the predictor? That is, what is this? So we can actually figure out things about the future, so to speak. So when we do the predictor, we need to set up a basic timetable. So what we're going to do is, first, we're going to say that t equals 0 will correspond to the first time that we took a measurement of the population, which was in 1990. So t equals 0 will correspond to 1990. And also, if you look at this, this is important, 10 years later, t equals 0 will correspond to the year 2000. So we're just setting up a way to meter the time apparatus for this problem. So this will be a very convenient way to do it. However you set it up, it's got to be consistent. So we'll just take the easiest path, which is this one. So now notice, if this is true, then we have y of 0, which is y sub 0, is going to be 27.76. And this is million, but we know that, so we've got this. So this implies, if we use the solution curve, at least initially, that y equals 29.76 times e to the kt. So when you look at this and you think about how we do this problem, you're thinking, okay, well, I need a predictor, and really the only variable that I want will be the t. So what I would propose here to make this exact computation is to basically use the laws of exponents and solve for e to the k. So we can write this way, 29.76, and then we'll say e to the k raised to the t power using the laws of exponents. And now we can effectively change the base and have a nice predictor without any decimals, without any approximation in it, to have an exact predictor. So now we use the second piece of information. So basically this will allow us to solve for this piece of the puzzle. So now we have what? We say y of 10 equals 2,000. So this implies, so basically we take the given information and feed it into the solution curve. So this says 2,000. Oh, sorry, ding, 33.87. We know 2,000 corresponds to 10, but I need the actual population. So 33.87. The beauty of mathematics, it says, wait a minute, you used 2,000 twice. So now this implies that 33.87 equals 29.76 e to the k raised to the 10th power, because 10 corresponds to 2,000. So now we're thinking, okay, well, let's go ahead and solve for e to the k. So let's divide both sides here by 29.76. So we have 33.87 divided by 29.76. So let's operate on this a little bit. Let's just move the decimals. 3387 and 2976. Now, one thing I noticed with this particular example is, notice here, you got 15, you have, and plus a 6, that's a 21. So that's divisible by 3. So here you have an 11 plus a 13. That gives you, well, let's see, what, 13, and then that gives us a 22. So that's a 24. That's also divisible by 3. So let's divide by 3. 1, 1, 2, 9. And then let's see, that'll give us a 9, a 27, a 9, and then a 2. So 1129 divided by 992, that makes the number just a little bit smaller. And again, you don't even have to do that. Leave it this way if you want. It's not going to change anything. All of these numbers are equal. They're exact. So now, when we do that, this equals e to the k raised to the 10th power. So now we can apply the 1/10 power to both sides. That is, take the 10th root of both sides. Equivalently, e to the k equals the 1/10 power of 1129 divided by 992. So just take the 1/10 power of both sides. Here, this will absorb, and this just gives us e to the k. That's a strange base, isn't it? Very, very interesting base. So now, by the laws of exponents, we've got the predictor. So we can fill it in right there. So we have y equals 29.76. Then we have 1129, 992, and then raised to the t power, so we get t over 10. So here is our predictor, exact, exact, no round off, using all the exact numbers from the problem. So when you're tested, I may ask you to type the predictor. A lot of you, again, you run to your calculator and you solve for k, and you got a bunch of decimals in your answer, and that's no good. That's no good. That's sloppy mathematics, and I don't teach that way. So now when you look at this, let's see here. Okay. Right, good. Yeah, I love how you all answer the questions. You all are so quick to answer questions. You're very good. So now the next part of this problem says, when does the population double? So let me move up the page so we have our predictor right in front of us. So this is our model. So for values of t, you can use this as a predictor. And then of course you can use your Google calculator to get a nice calculus approximation, and it will be the best approximation because there's no approximation in our predictor or in our solution. So now we'll say B, when does the population double? So that just means, okay, you know, we start out with y sub 0. So this implies, or equivalently, when is the population 2 times the initial amount? And we know what the initial amount is. It's 29.76 million. So we can just write everything in terms of y sub 0 if you want. So now, equivalently, 2 y sub 0, and I'll just replace this with y sub 0. It's the same thing. 1129 992 t over 10. So you're thinking, if you think back to college algebra, you've seen this before, and in some books, they just have the formula for it, which means that the initial amounts absorb. So now we see these just absorb. And equivalently, we have, in this case, 2 equals 1129 divided by 992 t over 10. So what I would suggest here is, like we did with the last problem, we don't want to use that base. That's a little bit untoward and kind of messy and just too much work. So just like before, like we had with the interest, we'll just say take natural logs, or base 10 logs if you like. It doesn't matter. I like the natural logs because that's going to get you used to what you're going to be doing in calculus. Maybe if you take a physics class, that they may be more focused on base 10 for particular applications, but it doesn't matter. So now we have natural log of 2 equals the natural log of 1129 over 992 t over 10. Now, of course, we have the natural log of the exponential, so the power can descend. So equivalently, natural log of 2 equals t over 10 times the natural log of 1129 divided by 992. Now you're thinking this is easy. We can just cross multiply by the 10 here and then divide by the logarithm term to solve for t. So what we can do, you can write it this way so it's kind of easy to see. We can say t times the natural log term, 1129 992 divided by 10. And so you're basically just flipping this number. So if you write it this way, it's a little bit easier to see the algebra because the logarithms get a little bit long. So now t will equal, again, when we flip it, we have multiplication by 10, 10 times the natural log of 2, and then, of course, the log term in the denominator, 1129 992. Now, one thing that's interesting about this problem is that you can see when we start looking at the numbers here, they're not divisible by 3, but I didn't do any further checking. So there may be some other common factors that are prime. So I just said at this point, it doesn't matter. But if you want to make it more beautiful, you can check those numbers. And now we have an exact time right here. This is the exact time for doubling of the population, exact. So when you do these problems and you send me WebAssign messages saying, well, I'm getting this problem wrong, I know why you're getting it wrong, because you're introducing round off error. And that's why I finally started doing this. Again, the same student, the same student was in the college algebra class mentioned the fact that, well, I'm having trouble with round off. I said, well, you know what? I can put an end to all of this and just say, let's do exact computation. And then at this point, when you do your actual approximation, you start with an exact expression that you didn't ruin by unnecessarily rounding numbers. So in this case, I'll say round, just to give you some formatting, round to 2 decimals. So let's go to our Google calculator. It's got our last computation on it, so let's clear that out. So now we can do in the numerator, we'll do 10 times, again, this is our calculus approximation, which is fine at this point. Like on the test, I could just say, give me the exact year, and that would be the end of the problem. I'm just approximating it so you can get some practice using Google. This is a great calculator. Divided by natural log of 1129 divided by 992, close. And this gives us 53. So we'll say approximately 53.580961. I'll just round it off to there, and then we can do our formatting that maybe WebAssign would ask of us. So if WebAssign said round to 2 decimals, then this would give us 53.58 years. So you're thinking that if you work in city planning, for instance, that's really a STEM job, because city planners are like utility planners or directors. They have to know mathematics. They have to know how to make predictions when it comes to budgeting. And you know, you think about it, okay, there's such a large umbrella with that. That's maintaining utilities, maintaining infrastructure, predicting needs for the future using these types of models. I mean, you certainly would think, okay, well, you know, in this, you know, number of years, we're going to have a doubling of the population. So we really need to take care of certain infrastructure needs. We need to improve some roads. We need to improve our water treatment facilities in this area of the city or whatever. So STEM reaches everywhere. I mean, before too long, you know, when we say this is STEM mathematics, it's going to bring in even more outside. You know, we can bring in a lot of disciplines in urban and regional planning, and also business, which requires an excessive amount of mathematics. I mean, STEM, when I say STEM, I think about computer science and mathematics and medicine and all of that. That just touches so many areas. So we're kind of stuck with it. So when we look at these types of examples, what we want to do is to work things so that we get an exact answer. And this just offers a different way of computing the predictor so that we have a nice model with no round off. And you're not tied to a calculator. The only time we do use the calculator is at the very end if we're required to, because this is the exact And if you were working with a client, they would feel much better looking at this, knowing that you understood what you were doing, than giving them a whole list of decimals where you were not actually very confident. So again, we want to work towards a nice expression that gives us no round off error, and then go to the approximation with the confidence that we have exactly what we need. Now, there's another example before we get to the cooling law. Well, actually, let's see, I can do this. Let me go ahead and do this half-life formula, and then we'll talk about the cooling law. So here's an interesting problem with radioactive elements. The half-life, those you biology scholars will know what I'm talking about. The half-life, and chemists also, of strontium 90, and this is not a very long half-life like carbon-14 or something, is 28 years. I mean, when you think of, thousands of years and stuff, that's why archaeologists like certain radioactive compounds that have really long half-lives. Is 28 years. It says compute the time for a 50 milligram sample to decay to 32 milligrams. So again, when you see the decay, you think growth and decay law. So there's no question. You don't have to come up with a new formula or something like this. I don't want you to just sit there and think, well, what do I do? Just again, look for the key words. So now, when we look at this and we think about what we have, let's write down all of the given information. So Y will be our quantity of this radioactive strontium 90. So now we have Y of 0 will be the original or initial amount, which is 50 milligrams. And we can go ahead and say, well, what about this half-life? So Y of 28. Now you're thinking we can just do 1/2 Y naught. We can just say Y of 28 will equal Y sub 0. We can call this Y sub 0 over 2, which is really 50 over 2, right? That's the initial amount, which is 25. So if you wanted to fill in the numbers, that's how we actually describe the half-life. What is the time? What is the time for half of any sample to decay to, for instance, what is the time for any sample to decay to half its initial amount? So if this were 100, then we would have 50. We have 50, so we're stuck with 25. So the half-life basically just describes the amount of time for half of the initial sample to decay. And so we have to use the given numbers in the problem. And so now let's write the predictor. So this implies, in this particular case, and I think it's interesting if you think about it, we can actually solve for our basic predictor. So we've got what? 1/2 Y naught equals Y naught e to the k raised to the 28. So with this equation here, we can solve for e to the k. Solve for e to the k. So of course the Y naughts, kind of like when we did the doubling, we were left with the 2, now we're left with the 1/2. So we really didn't have to use these numbers. It's probably easier just to use this. So this says if and only if 1/2, which we can write as 2 to the -1, the -1 will be easier for the base. So 1/2 is 2 to the -1 equals e to the k raised to the 28th power. And now we can just do the 1 over 28 power of each side. So if and only if e to the k equals 2 to the negative 1 to the 1 over 28 power. So of course the 1 over 28 here absorbs the 28 and we're just left with the first power of e to the k. So this will just run through with the laws of exponents, 2 to the negative 1 over 28. So this implies that we have y equals y sub 0, which again is 50. And then we have what? 2, put a little dot here if you like for times, 2 to the negative t over 28. So when we think about our model, again, we're just raising e to the k to the t power, because remember we have y equals y naught e to the k raised to the t power. So we simply substitute e to the k, 2 to the minus 128 power right here, and multiply by the t using the laws of exponents. So here is our predictor. It gives you an easy way just using the initial amount and the half-life. Just like before, the initial amount and the half-life give us enough information to, again, write down what we need. And of course, if the hypothesis changes, then the problem can be made more difficult, requiring you to take ratios. But I'm not going to do that to you. When I teach differential equations, sometimes I throw that in. But right now, I want you to be able to master these. And I think these are reasonable given what we've been doing in the class. And so now we need to know the t for 32. So now the new amount is 32. So we're thinking in this particular case that, of course, this is much greater or greater than the 25. So we're looking for a time that would certainly be less in this case than 28 years. So now we can solve. So solve. Our amount now will be 32. So we just substitute 32 here using the predictor. 32 equals 50 times 2 to the negative t over 28. So what's nice about these problems is that you can see formulas that just kind of fall out with these that are fairly simple. So now let's divide like we did before. So we have 32 over 50. So in this case, we can divide by 2. That'll give us what? A 16 and then a 25. Well, how interesting. That's a perfect square. So this is what? This is 4 over 5 quantity squared, right? How interesting. And this equals 2 to the negative t over 28. So now take natural logs. Take natural logs. So we have the natural log of 4/5 squared. And of course, we can bring that 2 down if you want. Use the power rule on this side. Just did that for grins, just because we can do it. And this will be the natural log of 2 to the negative t over 28. Again, power rule. So this gives us negative t over 28 natural log of 2. So now, if you like, and then of course we can run over here and just bring that 2 down. This will be 2 natural log of 4/5. So if you like, let's go ahead and do this in a user-friendly mode. So we have 2 natural log 4/5 equals, and so here we can kind of move the numbers over, t, and we'll do negative log 2 divided by 28, just so we have a coefficient for t, and so we can invert and multiply. So t, in this case, we'll just go ahead and move the negative up. So we have negative 28 times 2 ln 4/5 divided by log 2. And then, of course, what is that? What, a 6 and a 5? So that gives us a negative 56 ln 4/5 divided by log 2. Now, when you look at that, this is exact. This is the exact time, exact. This is the exact time for the decay from 50 milligrams to 32. So even though the computation is a little bit busy, it's not, none of the work is difficult. It's just kind of plotting through it. And so now, and you can use your Google calculator. We've used this several times already. Let's just go back to it and then knock it out. And then we'll do our cooling law. So let's clear out what we had before. So now let's go to our parenthesis and we'll do negative 56 times natural log 4 divided by 5, close the logarithm and close the numerator, divided by ln of 2. This calculator is very nice. And of course, you can use a keypad on your computer keyboard if you've got it. I just use the mouse. I mean, the keypad might be a little bit quicker. And this gives you 18. And I'll say in this case, let's round to 2 decimals. I'll write this. You'll see this when we get back to the document cam. Round to 2 decimals. So this gives us what? Approximately 18.02797. So let's go back to our document cam. So now you can see that if we use the rounding formatting, this will give us 18.03 years. So what's important, for instance, if you were giving a lecture, say you're a biologist or a biomedical engineer, and you were giving a lecture, then you'd want your work to reflect your ability to do mathematics and say, okay, we've computed our exact time. And then you pull up your Google calculator and say, well, let's give a nice calculus approximation to this. We are certainly indebted to calculus and the invention of the modern computing device, because it certainly does allow us to move from the exact to an approximation without excessive work. I mean, we would otherwise have to be using logarithm tables, and that would be fine, but it would take more time. And so the fact that we can use this to go here is really a big use of technology. So the work here is the mathematics, and here this uses the mathematics and the modern computing device to do some toilsome work for us for free. So this makes us a little bit lazy. So I don't mind that we use the Google calculator at this point, but it does make us a little bit lazy, but we'll deal with it. So the last model is Newton's law of cooling, and it's very similar to this one. Let me go ahead and write it down. So Newton's law of cooling. Same mathematician, Newton's law of cooling. Even though the previous one doesn't bear his name, he did discover it. Newton's law of cooling. Now, maybe to be a little bit simpler to you, let me go ahead and write the variables over here instead of and doing it the opposite of what I did before. U will be the temperature of object. So we say cooling, but certainly an object could be heating or whether otherwise, it doesn't matter. This is just how it's stated. We've got U to be the temperature of the object. This will be the quantity, so to speak, that changes. The temperature will change, so to speak. And then the K, like we had before, will be constant of proportionality. Let me move the cursor over here. There it is, of proportionality. And let's see, T, uppercase T, will be the temperature of the surroundings, the ambient temperature, so to speak. And U sub 0 will be the initial temperature of the object. Just like we had initial quantity, initial temperature of object. So again, even though I didn't say this before, when we have a differential equation with an initial set of conditions, that's sometimes called an IVP, initial value problem. So you'll see that used later on in your mathematics work, IVP, initial value problem, initial value problem. And you would think that many equations would be stated that way if the independent variable is indeed time. So for instance, here we have the DE, the differential equation looks like this. We'll say the instantaneous rate of change of the temperature of the object relative to time looks like this. It's the constant of proportionality times the difference between the object's temperature and that of the surroundings. So again, Newton observed this, and this is probably more of a law that makes sense to you when I write down the actual solution curve, because living in Texas, we certainly know what it means to have our vehicle sitting in the Texas sun, and then we go back to the car and we open the car and it's like a heat wave. Yeah, I mean, and then we're a little bit hesitant to sit down. If you got leather seats, it's like, okay, let's put a towel down or whatever. So the idea is that we are certainly aware of how temperature fluctuates, and this probably was maybe less difficult for Newton to postulate than the growth and decay law. And so, of course, here for the initial value, we'll say that the initial temperature will just be U sub 0, like we used before, with Y sub 0. And then the solution is also exponential. The solution looks like this: U of T equals the surrounding temperature plus this exponential term, U sub 0 minus T e to the KT. Now, why does this make intuitive sense? Because really what you're thinking is that this term will have to decay to 0, or at least converge to 0, because, like, for instance, if you set, we're going to do a turkey temperature problem. If you set something warm in a particular room, say that it's warmer than the ambient temperature, you set it down, you say within time, the object temperature will equilibrate with that of the room. I mean, you walk inside, you've been outside, in the summer, you're sweating, and you sit down and read a book, or check your email or whatever. Within a certain amount of time, you're not sweating anymore. Your temperature has equilibrated. At least, your body temperature will always be the same. But if you brought your books in, or your backpack or whatever, and you set your books down and all that, the objects that you bring in will equilibrate with the ambient temperature. So you would think that within time, the object temperature would be that of the surroundings. So this actually makes a lot of intuitive sense. So when it comes to, I just wanted to share with you before we do the problem, this is what you're going to learn in calculus. Just wanted to show this, that when you actually do this type of problem, this is what you'll learn when you take the calculus. So you see the solution curve here. And this is just, as I've written over here, a first order linear differential equation. So the computation is not difficult once you learn the calculus. So I wanted to show that to you, that that's what you're going to learn in the calculus sequence. And then, of course, when you take differential equations, you'll focus on the first order linear and spend a lot of time. Those of you that end up going into nuclear engineering will love your first order differential equations. They are the mainstay of nuclear engineering. So the idea here is that intuitively this makes sense. So what I want to do, what's weird is when I write these things down, I need to verify that this was correct. So I just solved the equation and said it's right, because I use a particular notation here that I think is user friendly. And so I wanted to be able to verify that what I remembered it to be was correct, but that's no good. I need to verify it, and I did by solving it. So now let's do an example. Again, you'll know this is cooling because the temperature will either be cooling or heating. So it'll be apparent from the problem that you use this particular rule. So this is called the cooling turkey. So we have, I'll just write cooling turkey. You've taken a roasted turkey from the oven. So let's just say this, roasted turkey is removed from an oven, and placed in a room, maybe the kitchen, at 75 degrees. So we have the ambient temperature, and then as an aside, when you remove the turkey, the oven temperature will say the initial temperature is 185. Of course, when we do degrees, when we define degrees in terms of radian measure in college, in trigonometry, we'll be talking about that. Pure numbers or not, that's always what we're interested in. And so now, at this particular case, let's write this down. The turkey temperature is 150 degrees at 30 minutes. What is the temperature at 45 minutes? So what we can do here is just go ahead like we did with the last one and write down all the given information and substitute that into the solution curve. So now we have T equals 75. We'll just put the numbers without the units, so to speak. And we've got U sub 0 equals 185. So this implies, if we use our solution curve, U equals 75 plus 185 minus 75 e to the k. And of course, we'll do the same technique, e to the k raised to the t. So equivalently, we have U equals 75. And of course, if we subtract, that's just going to leave us with a 10 and a 1. So 110, right? E to the k raised to the t. Now, of course, we need e to the k, so we go to our problem and see that we have another condition right here. So the turkey temperature, and I'll just say this, I left out the temp, the turkey temp is 150 at 30 minutes. So we know that U of 30 equals 150. So that's from this. And so that will allow us to solve for e to the k. So this will be equal to 75 plus 110 e to the k, again, raised to the 30 minutes. So now note, time is in minutes. So let's just go ahead and solve this. So now we've got what? Subtract here, 75 from 150 is 75. 75 equals 110. So we need a predictor, e to the k raised to the 30. And so now we have, if you like, let's just go ahead and do this. So we've got what, 5? So that's a 1. And let's see, 25, 5 times a 15. And then 5 here. That'll be a 2, 22. So 75 over 110 is factored, e to the k 30. If and only if, so now the 5's absorb, and we're left with 15 over 22. This is a lot more user-friendly number than the ones we had before. So 15 over 22 equals e to the k raised to the 30. So now we can do the 1 over 30 power, the 30th root, so to speak. So equivalently, e to the k equals 15 divided by 22 to the 1/30th power. So now we can substitute into the original solution curve. So u equals 75 plus 110. Now we'll just go ahead and substitute this in and then hit it with the t. So we've got 15 over 22 t over 30. So now you can see that when t is 30, this just gives you 1. And so you got 110 plus 75, which was 185. So that's a quick check that we did something correct. So here's our predictor. Now, of course, to answer the question, I mean, this is the hard work. That's the easy part. So when we look at this, we simply want to substitute 45 for t and do our Google approximation. So let's move this up and get another sheet. We'll use our predictor. So now in 45 minutes, so we have u of 45 equals 75 plus 110, 15 over 22. So we have 45 over 30. But of course, that's a 3 times a 15 and a 2 times a 15. So that'll give us a 3 halves. So 75 plus 110, 15 over 22 raised to the 3 halves power. So this is exact. So like on the test, I might say, okay, give the exact temperature. That's it right there, exact. Now, if I put an expression like this and you do a different computation, then you'll have to figure out which one is equivalent to yours. But if you just go ahead and do it the way I've taught you, you'll have less work and your work will have more integrity. It's amazing. I've shared my techniques with other mathematicians and they're like, well, that's different. I said, well, it's also correct and a better way to do it. And then they say, yeah, but usually it's like, well, I don't know, I'll just keep doing it the old fashioned way. But you know, that's really not the idea you want. In STEM, we're always moving forward. We're always rethinking things and making things better. So now if you go to your Google calculator, let's find Google again. So let's see here. What would we do without Google? I tell you, we Google it, whatever. Okay, so now let's see what we have. Let's go ahead and do the exponential part first. So we'll do 110 times, and then we have our parenthesis for our base, 15 divided by 22. So basically, we're just changing the base without trying to change the base. And then we go here to our exponent, and we want to have 3 divided by 2, 3 divided by 2, close. And then we want to add 75. And this gives us 136. I'll write this down. And in this case, I'll just say round to 2 decimals. So 136.9292. That'll be sufficient. So this will give us 136.93 degrees. So if we round to 2 decimals. So again, the answer is at least intuitively clear. Okay, at what do we have? At 30 minutes, we had 150. So we expect at 45 minutes that it will be a lower temperature. I mean, clearly our common sense would say that. And so this basically confirms that. So if we got, 179 or 5,000 degrees or whatever, we might have made a mistake somewhere. Okay, so now the last one is this. So what I want you to get from this is just maybe a new way of looking at these problems that you don't have to memorize. You don't have to memorize a single formula except the solution curves. You know that, and everything else you just do using basic algebra and the construct of the log and the exponential. So B, this is, again, we always want to do the backwards problem. When is the temperature, and again for the turkey, 100 degrees. So this is simple. We've already done this problem, but see, here's the key. Students always lament these problems because they know their technique might be a little bit shoddy, and they're like, oh man, I'm not really confident with this. This makes your calculations confident. You don't have to worry about any round off error because the only time you approximate is at the end. And I know I sound like a broken record. I don't apologize for it because when you start doing your mathematics better, then I'll be quiet, but that'll never happen. We never get there, ladies and gentlemen. We're always improving. We're always improving. I graduate from Texas A&M with an advanced degree in mathematics, and I'm like, wow, I know everything. Well, I don't know everything. So every year I teach, I do more research and I do different things. You're always growing. And so that's what, as a STEM professional, that's what you'll do every day. And then once you work for 20 years, you'll be like, man, look what I know now. And that's why you get a great raise. Your boss says, well, good job. You're going to get a raise. And then you can be a great philanthropist and solve the problems of the world. So there's all kinds of great things you can do with STEM. So now we take our predictor and we just say, okay, 100 is the goal temperature, and we replace U with 100 and do the backwards problem. So 75 plus 110, 15 over 22, T over 30. So now what you can see is you see why I spent all that time with the solving the equations. Because now when we do these types of problems, it's just like, okay, let's solve for T. So it's just an equation solving technique. Now, if I gave you an equation, it wouldn't be some ridiculous looking equation with a bunch of crazy numbers in it. It's going to have this refinement. So we're doing the same thing we've been doing. So now let's just go ahead and subtract 75 from 100. That'll give us 25 equals 110. And this will give us 15 over 22, T over 30. Now, when we look at this part, we're thinking, okay, now we need to divide by 110. So let's go ahead and do what we did before. We got 5 times 5. And then we have 5. I remember this, 5 times 22, right? Equals 15 over 22, T to the 30th. But now, of course, the 5's absorb. And we get 5 over 22 equals 15 over 22 t over 30 power. And now at this point, just like we've done before, our favorite log base, base C, take natural logs. So let's do it. So we have the natural log of 5 over 22 equals the natural log of 15 over 22 t over 30. Now, of course, we can apply the power rule and the t over 30 will descend, become a coefficient. So t over 30 times the natural log of 15 over 22. Now let's clean this up a little bit and move all the riffraff to the right to isolate the t. So we have a t. So this is natural log of 15 over 22 divided by 30. So now we can see, we can just invert and multiply. So now we've got what t equals. So we do the 30 upstairs and the log term downstairs. So we have 30 times the natural log of 5 divided by 22, and then division by natural log of 15 divided by 22. So again, this is the exact time. Now, of course, you know, if you were a detective or you worked in a forensics lab where you had to put information together, you know, for a court case, that again is the STEM profession. You know, there's so much glamour behind being a detective. It's not an easy job. It's a very hard job. And then everybody's, you know, oh, you gotta produce the right evidence. You know, I've got this client. Well, the thing is that uh, when you do forensics lab work and you become a forensic scientist, that again is a huge position, which involves scientific method, mathematical methods, just like what we're doing here. So now when you look at this, you can say, okay, well, here is the time that corresponds to a turkey temperature of 100 degrees. So now we can go back to our Google. So Google calculator. You know why I know about the Google calculator? When I was teaching a pre-calgebra class, which is the combination of college algebra and pre-cal, we couldn't get an honors course to make, but I had enough students that wanted to take honors, but they weren't, you know, it wasn't over 10. But one student said, "Oh, Professor Ron, let's use the Google calculator." I said, "What's that?" And he says, "Oh, let me show you." And he just pulled it up on his phone. And I thought, well, how neat, free calculator that works. So I thank my student for that. So we've got 30 times natural log of 5 divided by 22. Close the log, close the numerator, and then divide by the natural log of 15 divided by 22. Close the natural log, and this gives us 116, and we'll round to 2 decimals, 116.0549, and we'll round to 2 decimals. So back to Professor Ron's, what is it, document cam from Japan. I tell you, and I've told you this story before, but when I was looking for this, the only document cams that were available were international. There was not a single document cam available in the United States when we hit the fall semester. And I got this one in 6 days. So it came across the ocean. I mean, I couldn't believe it, but IPEVO. So if you ever do any teaching with Zoom and you need a nice document cam, I recommend the IPEVO. So this gives you, in this particular case, well, you know, we could do, you know, 2 decimals, that's fine. We'll do 116.05 minutes, which is fine. 1 decimal, 2 decimal, no biggie. So when you look at these types of examples, what I wanted to do today was just give you an opportunity to see how you can work these problems as equations, where you construct the actual equation for the specific problem from the solution curve. So like I said before, when you get to calculus, you'll learn how to solve this differential equation and then write the solution curve. That's what you do. That's why you take differential equations, because you see differential equations in science, mathematics, and engineering, and you need to learn how to spot certain patterns and then know how to solve it. And so this is a very famous type of equation. It's a separable equation, and it's also first order linear. So the idea here is that you will learn these techniques when you take the calculus sequence. And then, of course, when you take differential equations and maybe eventually partial differential equations, you'll use these techniques over and over. So I just wanted to share with you a way to look at these problems a little bit differently. Now, in closing, let's see here. I just wanted to write down one other problem to finish up. Here's our last equation from the logs and exponents. So we have log base 2 of x plus log base 4 of x plus log base 8 of x equals 11. So we want to solve in R. And this makes a nice closing problem. Now, of course, you're thinking, well, just combine them, Professor Ryan, you know, the product rule. But, you know, of course, we can't do that. We have different bases. So basically, we see that this is set up nicely to change both of these to base 2. So we change these two terms to base 2, and then we have one logarithm, and that's the best. So let's change these to base 2. So equivalently, log base 2 of x plus log base 2 of x divided by the base 2 log of the old base, which is 4, plus log base 2 of x divided by the base 2 log of the old base, which in this case is the base 8. So this is so easy now that we've been changing bases, but these are nice numbers. So we have log base 2 of x. So of course the base 2 log of 4 is 2, since 2 to the 2 is 4. So we get 1/2 log base 2 of x. And of course the base 2 logarithm of 8, 2 to the 3rd is 3. So we get 1/3 base 2 logarithm of x equals 11. So I thought this would be a nice thing to close with. So now you can see that we have a log base 2, log base 2, log base 2. So we do our factoring technique, even though this is not a difficult factoring. Just remember, in order to use the definition of log, we need one log term, and we can't combine logs that have different bases. So now we have the log base 2 of x times all of these numbers here. So we have the distributive law. So we have 1 plus 1/2 plus 1/3 equals 11. So let's get a common denominator of what? 6, right? 2 times 3. So we get 6 plus 3 plus 2. So this is log base 2 of x. And now when we add these numbers, we get a 9 plus a 2, which is an 11. Well, that's kind of convenient, right? Because it's going to absorb. So this is just a number times the base 2 logarithm of x. So we see the 11s absorb. So equivalently, we have log base 2 of x cross multiply equals 6. So again, this is this number, 11 over 6, times the base 2 logarithm of x. But of course, the 11s absorb. And so the power of 2 that equals x is 6. So x equals 2 to the 6th. But that's just what? 2 to the 3rd times 2 to the third, which is 8 times 8, which is 64. Now, of course, that makes sense here. And surely if you had looked at this problem long enough, you'd like, I figured it out, Professor Ron, that's fine. But this shows you now that when it comes to doing logarithmic or exponential equations, you simply apply identities and the definitions. And so we can't combine logs of different bases, so we change the base. And of course, this was nicely set up so we get nice numbers clearly. And then we move to this part where we say, well, what's the logarithm? It's the power of the base. So the power of 2 that equals x is 6, so x is 2 to the 6th. So again, don't look at these as being anything but what they are. And when you get to calculus, you'll learn extra stuff. And I've told all the students that come to conference hours, you're going to take all of this stuff, be on your shoulders. You know, you'd be taking all this weighty mathematics, and you just go to the calculus room and just throw it in the room. And you're going to use everything we've been doing now, and then you're going to add to it to make your problem solving even better. So I hope that you've enjoyed, you know, I know this has been review and maybe it's been a little bit boring, but I hope you've enjoyed kind of thinking about what you've done before and maybe reassessing it and moving it to a level where hopefully you have a better understanding. And then when you get to calculus, you'll have all the prerequisites you need. Now on Thursday, we're going to start trig, but just remember, the end of the week, I'll have an email announcement about the test, but there will be no trigonometry on test number 2. This way you can get all of your exponents and things done, which again, for most of you, all of you very much review, but you'll be able to start on the trigonometry and work with that, but you won't have the stress and anxiety of having to do that on the next test. So I'll reserve the trigonometry for the 3rd test, okay? Well, enjoy the cool weather, but not so cool. You know, we'll leave 11 degrees for Montana. We'll take 55, 40, 45, you know, but no more 11 degrees and sub-0 degrees. We're just not going to do with that. So let's just see who we have here. The test is going to be next week, the same time. It'll be open Thursday at 6 a.m., and then be due Friday by 11 p.m. So it'll be the same window of time that we had for the last test. And so, like I say, I want to give you a flexible amount of time so that you can get all that done, get it complete, then take a few days off during spring break, maybe study a little bit. I don't know, you know, sometimes it's like students say, I'm just gonna crash and catch up on my sleep. But I'm glad that you all made it in today, and I'll send out invitations for the office hours like I normally do. So if I see you, that'll be great. If not, I will see you at our next lecture. So everybody have a great day. Stay warm. Take care.